When a guitar string is stretched due to the tension, or when a femur is compressed due to some applied downward force, in either case, there's an elastic limit to the relationship between the stress and the strain on these materials. So in a previous lesson, you saw what a graph of stress versus strain looks like in general for all materials, whether it's a spring, a piece of rock, bone, steel, concrete. And the key part of this graph is the first part. As you first start to add stress to any material, there's a direct relationship between stress and strain, meaning the graph will have a linear shape. Now, if you stress it beyond that point, then additional stress leads to additional strain, but the graph goes nonlinear. That might still be within what we call the elastic limit of the material, but you've gone beyond what we call the proportional limit. So let's focus our study on this part of the graph, applying either tension or compression or any sort of stress so that we don't exceed the points for which the relationship between stress and strain are linear. Then in that case, there must be some slope to this graph, meaning there's got to be some sort of constant, and that constant is a constant of proportionality that represents the value of rise over run, the value of stress over strain. Now when it comes to a spring, we say that the stress is the amount of force and the strain is the resulting elongation of the spring. And so any ratio of stress over strain for a spring is going to be some number of newtons per meter. And those are the units we use to express the K value for any spring. When it comes to materials like guitar strings and bones, we're not going to measure the stress in force, we're going to measure it in force per unit area. So as the guitar string gets stretched, it's not just the amount of force that's applied, but it's a ratio of the amount of force in comparison to the cross-sectional area of that guitar string. And we're not going to measure the strain simply as the amount of elongation, so that would be some delta L. We're going to measure it as a percentage increase in the elongation. So there's an original length of the string, L naught, so the strain could be expressed as a ratio of delta L over L naught. So if that's the case, then stress over strain for a guitar string would be something like, stress over strain. This would be force per unit area divided by change in length over initial length. And we're going to call that ratio of stress to strain as long as we stay within the value where there's a constant proportionality, capital Y, and that stands for Young's modulus. So what are the units? Well, it's newtons per square meter divided by, well, there are no units for this, right? Because it's just meters over meters, and that cancels out. Well, a newton per square meter is known as a Pascal. So here's a table of constants of proportionality. In other words, the value of Young's modulus for a list of different materials: aluminum, concrete, copper, diamond. Now, we're given the units in GPa. What's that mean? Well, that's just gigapascals, right? Meaning times 10 to the 9th Pascal, meaning times 10 to the 9th Newton per square meter, and if you want, over meters per meter. Just as a way to remind you that the formula for Young's modulus is the force per cross-sectional area of material divided by the change in length over the initial length. And that's the same whether you're talking about a guitar string or a concrete pillar. If you want to support a heavy load, you might make a big pillar out of concrete, and as additional weight is applied, that adds force spread out over the cross-sectional area of the concrete pillar. So that's the value of stress, force per unit area, and the result is that the concrete becomes a little bit shorter. Now, I might have exaggerated how much shorter just so you can see it, and there's a value of delta L. So the initial length of the concrete pillar was L naught, and so the strain can be expressed not just as how much, but as a percentage, as delta L over L naught. So this is just an introduction to how we calculate values for Young's modulus. And keep in mind, Young's modulus is only a valid quantity if you stay within the proportional limit.